record. Doo-doo. So today's question, can we just look at GIFs? It is GIF, it's not GIF. If you want to call it a GIF, we can physically fight, but I don't want more blood on my hands, more bodies to bury. So I'm just going to forgo that and say you're wrong, and that's the end of story. It's GIF. So we're just going to look at GIFs today. We'll be successful when we can figure out how fast rates are changing as another rate changes. Oh, let's do it. Let's roll them up. Crack the knuckles. So I have a GIF for you. Here's an animated GIF. As you're watching this, I'll just give you 30 seconds to look at it. What rates are involved in this animated GIF? Think about it. I'll give you 30 seconds. All right. So as you're looking at that and noticing, there's probably a couple that you're noticing, but in particular, the ones I'm thinking about are the volume rate and the radius rate of the balloon. So a question for you. Of those two rates, again, the rate meaning how fast it's changing, which of the two rates is increasing at a constant rate, meaning that over time it's adding the same amount over time? So think about that. I give you 15 seconds. And if you think you know, volunteer can throw something in there. Otherwise, I'll volunteer someone with our victim creator. Ooh, a brave guess of both. Okay. Thinking both. All right. Let's talk about it and think about that. So if both are increasing at a constant rate, so as the radius goes from 1 centimeter to 2 centimeters, and from 2 centimeters to 3 centimeters, does the volume between 1 to 2 to 3 grow at the same amount? Let's look. So let's see, its volume of a sphere is 4, whoop, that's not that. 4/3 pi r cubed. So there's a radius of 1 centimeter. There's 2, so it's a growth of about 29. That's a growth of about 80. So a constant growth in the radius isn't going to give us a constant growth in the volume. And that fact, that's an increasing growth for the volume there. So that's something kind of wild and crazy that I wanted to point out. And I'm so thank you so much for your bravery and throwing out those ideas, because I think that's an important thing to think about. And I think a lot of people just assume that. And by using a little bit of math, we can verify, well, that's not the case. Both can't be increasing at a constant rate. They're both increasing. If the radius is increasing at a constant rate, the volume is increasing at an increasing rate. It's growing more and more and more every time. Like, for instance, what happens at 4? That's added another 150-ish. So we went from adding like 29 to 80 to 150. So it's growing. It's growing more and more and more every time. So if the radius is constant, the volume is going to keep growing at a greater rate. But what if the volume was growing at a constant rate? Would the radius increase over time or decrease over time? Or I'm sorry, let me rephrase that. Would the radius length, would the rate the radius changes increase as time goes on or decrease as time goes on if the volume is increasing at a constant rate? Trying to think. Decrease. Decrease is the way it should be. And I was just working on getting something set up to show you. To the 1/3. So there's the radius with a volume of 20 cubic centimeters. If I go to 40, it's increased by about 0.5. If I increase the volume by another 20 to 60, it's increased by about 0.3. Yeah. So because the larger the radius gets, the more volume it'll take for it to grow. So if the volume keeps growing at a constant rate, the radius isn't going to move as much. And we can kind of see that with those numbers right there. So we already talked about that. There's also the alien ship and the pirate ship. And we could talk about both those ships and all the ship that goes along with that. But we're not going to. There are some things, and we could if we really wanted to spend the time to look at that. Here's another GIF, because looking at animated GIFs is never complete unless there's a cat involved. I also made me think of this one. So 2 questions I have to ask about this. Like, you use the cat one as the reference, but that one's kind of hard to see it as. It's a little bit easier to see it on the other one. What happens to the speed of the roll over time? Or rather, it's a related but slightly different. What happens to the rate the radius is changing over time? Is it increasing, decreasing, staying the same? So yeah, the rate, well, let me think about how. So the radius is decreasing over time. I guess what I should be saying is the rate it's decreasing. Is that is it decreasing faster and faster over time, or is it decreasing slower and slower over time? Assuming that it's coming off at a constant rate, like it's coming off at like 10 squares a second. If it's coming off at 10 squares a second, is the radius going to get is it going to get smaller? Is it going to get, definitely going to get smaller, but the rate it's getting smaller, is that rate is it going to get smaller faster and faster and faster? Or another way to think about it is the roll. As more and more squares come off, it might, and that's the thing with the cat, is that there's an initial thing there and then it starts slowing down. But with the toilet one, like, it's pulling it down at a constant rate. The idea is that it should speed up over time. Like the speed the roll's going goes faster and faster, because if you're taking 10 sheets or 10 squares a second, like 1 second, but then 2 seconds later, 10 sheets is a lot more of what's left than it was originally. So I responded to Lizzie's idea. That's the right idea there. And then Evelyn, you're right. It would start off fast, but it would slow down because the cat's not constantly pulling it. It's like there's an initial momentum thing, a moment of inertia, and then it just starts slowing down over time. But if this one, is pulling at a constant rate, in theory, it should keep going. Cool. Wow. All right. I kind of flew through that. All right. So here's another one. There's some more rates going on. What different rates can you see here? So my pod thankfully tested negative, so that's good. We weren't super sure. I got a little scratchy throat, and we were worried that there was a false negative from the people before, but so far everyone in our pod has tested negative, so that's good. So what rates are there? Oh, so the further the sauce gets to the middle, the faster the radius shrinks. It's true. The rate at which a saucy thing is moving inward, the spinning of the pizza, the rate of the tomato paste going on the pizza. I think those are all some great rates to talk about. Like, how's the radius changing over time? How's the saucy dispensing thing going? How fast is the pizza thing going? How fast is the sauce coming out? There's a bunch of different rates we could talk about here, and they're all related. They all affect each other. I mean, if they're all constant, there'd probably be some messes, some giant messes, and this wouldn't work out as well as it could. So being aware of how things change in relation to each other is an important thing. Even though I think most people just kind of glop on the middle and spoon it out, but then you didn't have to like do anything. It just did. It just goes. So we could spend the rest of the class debating some more things. Like if each of those I had 3 different rates I was thinking about. I was thinking about the sauce rate, the arm rate, and the rotation rate. But we definitely talk also about like the radius of what's left or the volume of the unsauced area or the area of the unsauced area. There's a lot of different rates we could look at. I picked 3 that I wanted to talk about, but we're not going to talk about them right now. So to keep moving on, here's a recap of implicit differentiation, of just generally solving an implicit differentiation problem. You start off with differentiating with respect to some variable. Usually pick x, could be t, could be something else, but usually it's x or t. And when we do that, there's usually a dy dx that shows up somewhere, or dy dt that shows up somewhere. So we really want to try to get all of those to a single side. Then we want to try to factor out dy dx from everything that has it, and then divide by those terms or that factor, so you can get dy dx all by itself. That's generally how we solve an implicit differentiation problem. There can be more to it, but that's like general heuristics about where to start and where to go. Related rates. Here's our Google definition. And honestly, it's a pretty decent definition, which is why I keep coming back to it. In differential calculus, taking derivatives, related rate problems involve finding a rate at which a quantity changes by relating that quantity to other quantities whose rates are known. The rate of change is usually with respect to time. So there's a couple things I want to point out with that. So here's kind of a general relationship you could use. There's a rate we know, a rate we want to know. And there should be a way that we can relate those two things with some other equation, this position A, position B thing. Don't super worry about that right now, but I'm just saying like there should be an equation that we could differentiate in order to get both the rates that are important here, the one we know and the one we don't. But again, this is generally how we're solving our related rates problems. We're going to write in an equation, then differentiate with respect to time. Differentiate with respect to time. Related rates are just implicit differentiation with word problems. There's slightly more, but basically that's it. That's what we're doing. So here is what I'd like to do. Boom. There you go. So I would like to kind of look at this and talk about the first couple parts with you. So please open that up. We're going to do one of these today, and then I'll ask you to do 2 of them in addition to your practice, just because by doing them, you'll have the resource and you can work with that. You can try typing right on there or not. It's up to you. I would maybe just look at it and then write it on your paper. And if you want to print it out, if you have those abilities, that might be a good place to go. Normally, I made this resource page for you. So, okay. Here's the setup. So we're going to go through the different parts and just kind of talk about it. So I have water leaking from my condensate pump. Oh no, that is a picture from my condensate pump, by the way. It's leaking at a rate of 2 centimeters a minute. How fast is the radius changing when the puddle is 18 centimeters across? Now I know the puddle is always 0.2 centimeters deep. Now we're going to assume the puddle is a cylinder. So we're going to write an equation for the volume of a cylinder and make sure we understand what each variable stands for. So the volume of a cylinder is pi r squared times height, because it's the area of the base times the height. So I make a note of that. we have three different variables there. We have volume, radius, and height. One of them is constant the entire time we're dealing with this, and that's the height. So we could rewrite the equation like this. Now the equation is kind of in an ideal spot because we have two variables. And we already know one rate. Drawing. We know a rate right here. This rate, we're going to call dV dt, because it's the rate the volume changes as time changes. So dV dt is 2 centimeters cubed a minute. The thing we want to know is how fast the radius is changing. That we're going to call dr dt. How does the radius change as time changes? And we don't know what that is yet. There's one other piece of information that's going to help us out in this. And let's point that out with orange. This right here. Now, what is the radius when the puddle is 18 centimeters across? Is it 18? Oh, where'd my mouse go? Oh, there it is. Or is the radius 9 centimeters? Those are all the things we know and want to know at the moment. Sweet. So now we have this. What we're going to do is we're going to take the derivative with respect to time to both sides. Let me get this. So there's a little piece in between where I actually show the setup of the derivative. I just didn't do that here. So the derivative of v with respect to time is going to be 1 times dv dt. For the second part, well, the only variable on the right-hand side is r. So I'm going to do the derivative of r squared with respect to time. So the derivative of r squared normally would just be 2r, but because r isn't the same variable as t, or again, we're assuming r squared is a composite function. So I get laser pointer. So r squared, the derivative of that's going to be 2r, but I also have to multiply by dr dt. And we're still multiplying by 0.2 because it's just a constant. You could try to use product rule on this and look at it as 1, 2, 3 different functions. But the derivative of pi with respect to t is 0. The derivative of 2 with respect to t is 0. And those other pieces will just go away and is a lot of unnecessary work. At this point, we can start plugging stuff in because of the 3 variables up there, dv dt, r, and dr dt. We know 2 of the 3, which means if we plug in 2, we can figure out the third. So let's plug in the things we know. dv dt right here was 2 cubic centimeters a minute. The radius is 9. Now we just have to solve for dr dt. That's just algebra from there. And so dr dt will be in centimeters a minute once you solve that. I'm not going to finish solving it because I believe in your ability to handle solving for dr dt there. Let me clear that. Here, let me actually go back first. What questions do you have before I move on to the next thing I'd like you to do? I'm having fun. Okay. I'm going to clear annotation. So there are 3 more problems. There's an oil spill problem, a happy cube, and a companion, or happy square and a companion cube. What I'd like you to do is, if you have the opportunity right after this class, try to do the first 2 sometimes. Oh, I know what I was going to say. The next 2 problems, the happy square and the oil spill. I'd like you to try to do those 2 on your own before I see you next Tuesday. Again, they're very, very similar to this puddle problem. All right. And as you try them, I have my work up here so you can check your work. So you can come back and look at this. I don't have this one because we're going to start off on Tuesday with this one. So there's a part 2. So this is your actual thing that's assigned and due. This page that I gave you is a resource page. It's where we can do a couple of these to kind of get going. Related rates, especially virtually where we can't just collaborate like easily. We were doing something a little bit different. And yeah, so that's what we're doing. The resource page I'm not going to collect or even look at. It's for you. The idea is that I'm asking, try these 2. You can check your work. Like I have worked out solution right there for you that I know is correct. So I would love for you to please do that. And there's 2 parts to the homework. There's the first part. There'll be separate assignments, by the way. I haven't put them in Schoology yet, but they will. This one, there's more problems, but they're a little bit easier. And then there's a part 2 that there's fewer, but they take a little more time. So be aware of those things. Make sure to read the book, work through that stuff. And that's what I had for you. Now, before you go, here's what I like to do. I've held a couple Discord chat sessions to help folks out just with whatever math calc questions you have, or just any questions really. But I've been holding them at 3:00 and I've got 1 or 2 people, and which is fine. Like I don't mind. But I'm looking to try to see if I can set a different time that might work better for more people. And then try to do it on a semi-regular basis. Maybe not every 8A, but maybe 1 or 2 8As a week. I just want to try to figure out something that I'm not just sitting there waiting for people without knowing whether or not it works for people or not. So if before you leave the meeting today, what I'd like you to do is just private message me a time in the afternoon that would work better for you if I was going to set up like just a drop-in time. It doesn't have to be not necessarily today, but just like any day of the week. Like, is there a particular time, Monday through Friday, that would work best for you for a drop-in time? So you may leave as soon as you send me a private message about what time of the week would work best for you. Okay. But that's what I have for you. Again, there'll be a little quiz on Friday on stuff up to at least 2.6. So Greta, what time? Message me. What time works best for you?